All right, here we're going to learn about node analysis. And this is one way to solve a circuit. And when we say solve for a circuit, we mean pretty much define all the voltages and currents within a certain circuit. So here we have a picture of a circuit. We're going to go through the steps for node analysis. So the first, what we're trying to do with this, if we're trying to set up mathematical equations, turn this circuit into a system of equations with a set number of unknowns and a set number of linearly independent equations, so we can solve it like a math problem, and then we'll know all the voltages and the currents in the circuit. Okay, so let's say we have a circuit like this. What do we do first? Well, we have to figure out our number of unknowns. So what are we trying to solve for? And nodal analysis means that we're looking at each node and we're going to be using Kirchhoff's current law at each node. This is a systematic process, so it makes it a little bit easier to approach a problem that may seem difficult at the beginning. So the first thing to do is to determine the number of unknown nodes. All right, so for example, in this one, we have to talk about one thing first. If we look at this, there's one node on the bottom. There's a node here. Should I color these? Sure, you guys, why not? Let's use some colors here. We have one node on the bottom here. Oh no. One node is here. One node, oh gosh, yellow is here. Green, one node is here. Lighter blue here. Okay, so technically we have 1, 2, 3, 4, 5 different nodes here. So we would start out with, I guess 5. But what we're going to do is, and I'm going to put this kind of as an aside here. I'm just going to write in any color. It's going to be colorful. We have to pick a reference node, which is v equals 0. And so one of them, usually one that's kind of, when we draw it often at the bottom, but it doesn't have to be. In this case it is, and so all of these are kind of connected to here. And we also have a voltage source that's going from here to a higher voltage. So just because we're used to working with positives, it's nice to make this node 0. So this little ground symbol, that means the voltage here is equal to 0. So that gets rid of one of our known unknown nodes, because now we've defined it. So this one down here is 0. We still have 1, 2, 3, 4 left. By just looking at this, you can say, well, if I know this is 0, I have an independent voltage source here. And if we know one side is 0 and we know the voltage source value, we know the other side. So that's an intuitive approach. Another way is to look at the source suppression. So if you're not quite sure how many nodes are left, what we can do is suppress the source. And so if we were to suppress these sources, let's use a different color here. We'll use this purple over here, sure. If we were to suppress these sources, remember that this would become 0, so this becomes a short. Draw that in, and then this would become an open. I'm just gonna draw X's, so nothing is conducting there. And then what we would do is count the resulting nodes, and this time you see that this orange one is now connected to 0. That would be a known one, so that kind of gets absorbed into that one for counting. What we're left with then are 3 nodes, the yellow, green, and the blue, which we can then name V1, V2, V3. So I'll just say you can suppress sources. This is to identify my unknown nodes. Okay, so in this case, we have 3 unknowns, which we end up calling, in this case, yeah, v1, v2, and v3. The next step is to set up equations for this. So then we will use use KCL, Kirchhoff's current law, to set up equations. And they are linearly independent, but I'll just put equations here. And it's at each unknown node. Okay, so what we can do then is say, okay, well, we look at each of these, and I'm going to go ahead and erase this, the suppression, because now we've done the suppression step just to kind of understand what's happening. We don't need it anymore, so we can get rid of that. I'm going to erase this without erasing. Okay, perfect. And now we want to set up KCL at each of these, and I'm going to try to use, I'll use black in this case. And what we do is say, okay, so in V1, we're going to look at KCL, Kirchhoff's current law, and we want to either use current going into this node or going out to. This is just a good convention. I prefer to use going out of the node, and I'll just show you why, because I think it just makes the math a little bit simpler. We are going to use current out of this node, and I will draw it correctly this way. So current going out here, out here, out here. And then we're setting up the KCL for that. And we're going to do each of the equations for the current out of the node. So the first one is going to be V1 here. Sorry, the current branch out here. And so what we do is pretty much have the current, the value we're trying to find. We use Ohm's law. So V1 minus the other side. We happen to know that it's already Vs, so we can just use Vs here. And Vs is a given value, so we already know that value. And then we divide that by Ra. And so that's the current, because we just use Ohm's law. So then we add that to the current going down to the bottom. And so you have V1, it's going to 0. We already know that node, so it's 0, and that's Rb. And then plus this voltage V1. On the other side of this resistor is V2. That's an unknown, but it's okay because we've defined V1, V2, V3. We're going to solve for all of those, so we can use those variables without a problem. So we'd have V1 minus V2 divided by Rc. And the last one would be, and it's the current coming out of this node, Is, it's a current source. It's going the opposite direction, so it's going to end up being a negative Is. Okay, and let's go to the next one real quick. This will be faster because it has fewer ones. So now we evaluate KCL, and now pretty much ignore everything we already did in the other one. You can do each of these independently, which is why it's a nice way to break down the analysis. So here we have 0 at V2. This voltage, we're going to have currents out of here, here, and here. So we're going to have V2 minus V1 over Rc. The next one, V2 minus 0, because it's going down, over Rd. And then plus V2 minus V3 divided by Re. And that's the equation. We're going to go to the next one, then I'm going to point out a few things here. All right, so let's circle this node here just so that we can visualize it more easily. Let's start from, I'll start down here. So we have V3, so again 0 because we're using, everything has to sum to 0. V3 minus V2 equals, divided by Re, and then plus the current going downward here, so that's V3 minus 0 divided by Rf. And the last one is the current going out of here. We know it's IS because it's an independent source. So we have that value there. So you may notice that there's kind of opposites here. So we're kind of defining the current into and out of each one. It's okay because we're just, they're currents going in the opposite directions, but they're affecting each node in opposite directions. So that's why they're there. But once you've written these all out, these are independent. And you may say like, oh, these are too many different things. What am I solving for? Well, let's circle what your known values are first. So I'm going to underline the known values. So this is a known value, known value, known value, right? Those are just given. All the resistors are known. So no problem. You just plug those in. IS is given to you. VS is given to you. And IS as well. I think that's it. The rest of them, we're going to circle in purple. Those are unknown. So V1, 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 and then V2. And notice these all have V2s because they're all relative to V2. We have a V1 and a V3. And this one is V3. Everything's relative to V3. And then a V2 as well. So the purple ones are your unknowns. You have 3 of them. But then you also have 3 independent equations, KCL, applied at different nodes. And so you have 3 variables, 3 unknowns. And so then you just solve for the value using math. So I'm just going to write this down here at the very bottom. Solve system of equations for unknowns. So actually this is these are the basic steps for solving a equation with just resistors and voltage sources. In this case, the voltage source is connected to your reference node. Okay, so if you have this setup, you can easily determine your unknowns. First, you have to pick your reference node, suppress any other nodes to identify the unknowns, or you can just use logic, whichever works for you, as long as you get to the answer. And then once you have your unknown variables, you set up each KCL for them, and then you have 3 unknowns, 3 equations, and you solve your system of equations for your V1, V2, V3. Then you'll know all the voltages. From there, if you need any voltage current between any nodes, you can figure that out using Ohm's law, and then you're able to solve the entire circuit. So that's the simplest version of node analysis.